Brian,
Charles,
how you doing?
it's been too long.
It's been way too long. You're in a new building now, working on some special secret project.
Yeah. You know, as usual, I can't say much about it, but I can sort of lay the groundwork for this and give our Niners some inkling of what might be coming up in the future.
Okay.
So let's begin with a simple fact that in the opinion of a lot of people, sometime last year, October, November, theoretical physics was finished.
Finished?
Not in the sense of being, annihilated or wiped out, but meaning that the last piece was put into place.
Interesting.
Now, I know that this kind of thing has happened before. People have said this kind of thing before, when Newton wrote down his laws of motion, the first law, F equals ma, this one, things continue in a straight line unless impinged on by a force, and F equals ma, the second law, and equal and opposite. That was it. Theoretical physics was finished. We knew how to calculate the orbits of the planets to extraordinary precision, and there wasn't really anything left to do. Scientists could all go home and go to sleep and take a nap, retire to Portugal, and
nice.
But then this pesky thing came up called electromagnetism, and it didn't fit. And people, if you wave a magnet through a coil, then you get a current through the coil, and Faraday and Ampere and these guys started coming up with these sort of pesky phenomena that Newton didn't have anything to say about at all. So the next thing that happened is somebody had to figure that all out, and I don't know, it probably took a better part of 100 years, and finally James Clerk Maxwell published his equations. So the theoretical physicists all had to come out of retirement and get back to work, and from there the trajectory led straight to Einstein, because the equations of electromagnetism don't mix with the equations of mechanics. They don't mix with Newton's laws at all. In particular, if the equations of mechanics, Newton's laws, don't depend on how fast you're moving. If you're inside a rail car, exactly the same equations. You get exactly the same equations as if you're outside a rail car. You can't really tell.
Okay.
Well, when you apply these kind of transformations, where you convert the coordinates of an object into coordinates that you would measure in a moving rail car, the equations of Maxwell go completely haywire. In fact, they tell you, the equations, if you believe them, and they're extraordinarily accurate for things like anything to do with electromagnetism, with radio, light, photons, everything. Well, not photons. I'll get there in a minute. I'm trying to give you the quick, hand-wavy history of all of theoretical physics, so that I can persuade you that theoretical physics is done. It's completed.
Wow. Amazing.
So we've got Newton's laws, and we've got Maxwell's equations, and then we found out that Maxwell's equations don't transform the same as Newton's laws. They go haywire, and they tell you strange things. They tell you that if you measure lengths in if you look at a moving rail car and measure the lengths of objects from your standpoint outside the moving rail car, they squish. And they also tell you, the equations tell you that clocks go slower inside the moving rail car as measured from outside. Of course, the scientist inside the moving rail car thinks the same thing about you. He thinks, because from his point of view, you're the guy on the moving platform going the other way. So your lengths are squished and your clocks are running slower. So something is really strange going on here, right? This is theory of relativity. That's why it's called theory of relativity, because your measurement of lengths and times are dependent on your reference frame. I think it should be called the theory of absolutes, because what it really means is that you must insist that the laws of physics have exactly the same form. Instead of your point of view being, my measurements depend upon my point of view, you should say, my equations don't depend on my point of view, and then adjust your thinking. It means that the measurements change, but the laws stay the same. So Einstein worked this all out, and that's the theory of relativity.
Yeah.
And then we go to the next step and we say, well, the laws of physics shouldn't depend on things like how deep is my gravitational field. Well, we know the measurements do. There's a famous experiment where you put an atomic clock on the 7th floor of a building, you put another atomic clock on the 1st floor, and guess what? The one on the 1st floor runs slower than the one on the 7th floor. Atomic clock's very precise. You can bounce signals back and forth between them. In fact, you just do interferometry as the way to amplify the precision of any of these experiments. But you find out that the deeper you are in the gravitational field, the slower your clocks go. Sounds like relativity again.
So if we all move underground, we'll live longer.
Well, only from the point of view of somebody who isn't there. Darn it!
Bummer.
Bummer. So no, there's no free lunch,
Sure.
as usual. So, from the point of view of saying, well, wait a minute, it's not the relativity of the measurements is not the important part. What's the important thing is the absolutism of the laws of physics. They must be exactly the same wherever you are. The equations have to be, and so this leads you into a whole bunch of complicated mathematics involving differential geometry and curved spaces. And everyone's seen those diagrams where the gravitational field makes curved space-time, and the rays of light bend around things and stuff like this. So that gives you the general theory of relativity. The special theory of relativity is just things in uniform motion. How to account for the fact that Newton's laws and Maxwell's laws of electrodynamics don't work together. They don't play nice. You fix that with special relativity. Then you go to the next step and you say, well, gravitation doesn't play nice, and you fix that with the general theory of relativity. Meanwhile, you've got these I'm almost done.
There's no rush.
Oh, okay. Because I want to get to the good stuff.
Sure.
What's the secret sauce here?
Yeah, what's going on?
So I'm halfway done. We have gravitation, we have electrodynamics, and we fit those into a neat scheme together with the general theory of relativity. That's all figured out, works great. Every time anybody does any experiments, the answers come out to fabulous precision. A couple of the really famous ones are precession of the perihelion. I myself worked on time differentials for GPS clocks. Some of the GPS satellites are at slightly different altitudes, and they ride the geoid, which means over the
geoid.
Ride the geoid. They ride this roller coaster out there in space.
Nice.
When they go over the Andes, they sort of go down because the Andes are dense, and they create a gravitational well so the clock, the GPS satellites go up and down. They ride these lines. It's not at all a nice elliptical or circular orbit that they take. They bounce around. And you have to account for the fact that when they go, the clocks at two different altitudes run at different rates. Because they're atomic clocks on board those things, are very, very accurate clocks. That's how they do their magic. And if you don't account for that, it goes way off. I mean, we're talking millimeter precision, but it's still, you have to account for it. Okay, so we got two taken care of, gravitation, electrodynamics, taken care of by general relativity. Meanwhile, you got these pesky nuclear physicists who are finding out strange things. And the atomic and nuclear. The first strange thing they find out is that atomic spectra have lines in them, which means that the energy levels of electrons orbiting the, quote-unquote, orbiting the nuclei are quantized. And you get the development of the whole theory of quantum physics, which goes off in a completely different line than the theory of relativity. Theory of relativity is all based on how do you lay down coordinate systems on these curved spaces. It's more akin to cartography than it is to wave equations and things like that. It's just defining coordinate systems and how do you transform from one, like from the Mercator projection to the polar projection to Laplace square, all of these different kinds of map projections. In quantum mechanics, you solve wave equations because the weird thing about the quantum world is that particles act as if they go, when they go from point A to point B, they act exactly as if they consider all paths from point A to point B simultaneously. This idea, so this is just a fact. This is the way the world works. Nobody has any deeper explanation for it. If you try to explain it in intuitive terms, you go completely off the deep end.
Okay.
And plenty of scientists have. You're much better off for your sanity if you just say that's the way the world works, and it's extremely weird. But even though it's strange, but it's not mysterious. Mm-hmm. The difference between strange and mysterious is mysterious, we don't have any idea how it works. Strange means we know exactly how it works, but it's really weird. It doesn't fit any of our ordinary intuitions. Quantum particles don't act like pool balls on a pool table. They act like waves. When they're traveling, they act like waves. And waves can go everywhere. A water wave goes everywhere in the pool.
Absolutely.
But a particle only goes from point A to point B. So the way the quantum world works is when particles are traveling, they act like waves. And when they interact, they act like billiard balls. They do an instantaneous transfer of all their momentum and energy and other quantum numbers like color and flavor and strangeness and charm and all of these other things.
Interesting.
So over the years, the nuclear physicists figured this all out, and they came up with a bunch of different equations. But basically, the rough idea is there are two kinds of nuclear forces. There's a strong nuclear force that holds the nucleus together, keeps the protons together who are all positively charged and trying to burst apart. Well, there's a stronger force that holds them together. That force does things like convert neutrons into protons and other stuff like that. Then there's a weak nuclear force, which accounts for one of the kinds of decay that you see in nuclear reactions. Over the years, the weak nuclear force was shown to be an aspect of electrodynamics. That means there's this tie-in between, electrodynamics plays nice with mechanics because of relativity theory. Electrodynamics plays nice with quantum mechanics because of this electro-weak unification. But this unification, this law of unification, was of a completely different kind from the others. Mechanics is all about solving differential equations of time. Relativity is all about defining coordinate systems and curved spaces. Quantum mechanics is all about solving these wave equations. They don't even look like the same kind of problem. They're just, what's the relationship? Well, the relationship comes from, ta-da, something like Rubik's Cube.
Nice.
The way that the weak nuclear force and electrodynamics were unified was by noticing that the equations themselves obey laws of symmetry, which means if you transform variables inside the equations, or the equations themselves in a larger sense, they obey laws of symmetry. What's a law of symmetry? Well, it's something like if you take a Rubik's Cube and you do some rotations. Already this is starting to look like a mess, although you can still see some regularity in it. If I keep going, get a little shape that's symmetric, right? This is pretty nice. This means I can describe the states of the Rubik's Cube by describing the symmetry laws that hold when I do operations like this. There's a symmetry law that holds. It means the symmetry law is very simple. 4 things here. When I do a twist, those 4 things move over here, and vice versa all the way around. If I combine that with something like this, oops, I'm starting to get a mess. I don't want to mess this up because I don't want to embarrass myself on Channel 9. Yeah. Oh no, get out my cheat sheet. But
yeah.
And now we go back to one of our favorite themes from programming languages: composition. You need to be able to compose symmetries. Here's a different symmetry. What did I do? I didn't lose everything, but I mixed it up somewhat. I mixed up some of the colors with some of the other colors. And can I get back? Well, yeah, maybe. Oh no. There you go. I got back. Good. All I did was just compose one set of operations with another set of operations. Well, it turns out that the symmetry laws for Rubik's Cube are pretty rich. There are many states of Rubik's Cube, and you can, but you can solve it in just a few moves. How come? Compositionality. Remember our old theme of how to control complexity, the way to control complexity with compositionality? Yeah. Turns out that there are just a couple of ideas that you need to memorize. One of them is called conjugates, and the other one is called commutators. If you memorize a couple of rules, you can calculate all the rest of it from here. And this, people who are good at this, they practice. You know, I don't care what anybody says. It takes practice to get good at solving these things. Well, turns out the laws of physics obey symmetry operations that are very much like the symmetry operations that manipulate Rubik's Cube. And those symmetry operations were completely worked out in the 1950s and 60s for the strong nuclear force, for the weak nuclear force, for electrodynamics, and of course mechanics, which is just an approximation. So Newton's laws are sort of, we don't have to worry about them. We have to worry about gravitation, strong nuclear force, weak nuclear force, and electrodynamics. Because gravitation is Newton's laws turned into gravitation. So they're completely subsumed by the general theory of relativity. So we got these four things, and three of them are unified.
Okay.
How are they unified? By symmetry laws. In other words, just write down all these transformations that you can do with, here, let me do another one that's fun. This is an elementary transformation that lets you do all kinds of interesting things with the cubes. What I did there was swap the red edges with the orange edges, but it forced me to swap these guys too. So you see, these symmetry rules include constraints. You can do some things, but you can't do them completely free of other things.
Interesting.
Same is true for all the physics. That's why the physical world is constrained. You can't do just anything you feel like. It doesn't bend to wishful thinking. It's absolute, because the law. I like to call it the theory of absolutes.
Interesting.
Because calling it theory of relativity focused on the wrong thing. Laws of physics same everywhere, for all time, so far as we can tell. We look at galaxies very, very far away, and we see the same spectral lines that we see from atoms in the laboratory here. And all the evidence is that the laws of physics never ever change. They're exactly the same everywhere, and for the entire past and for the entire future. Okay, so we got these three: strong, weak, electrodynamics, and gravitation is outlier, doesn't fit. And there's this kind of a theorem that says it can't fit, because the symmetry laws for gravitation are, it's called the Poincaré group. And it doesn't fit in with these others. These others are unitary matrices in 2 and 3 dimensions, SU3, SU2, and U1 cross SU2, I think, is the electroweak unifying group. So these are groups of symmetry operations. The symmetry operations all fit in a group, which is an algebraic structure, which means you can never get it out. It's like a monoid. Remember our old monoid thing? Once you get in, you can't get out.
Hotel monoid.
Hotel monoid. Okay, so I'm going to drop the shoe now.
Okay. What's going on?
An out-of-work hippie physicist. I don't know the guy. He'd probably object to my calling him a hippie, but lives in Maui. He's a surfer dude. He stumbled across it. He found it. He found the way to put gravitation in with the other guys. And he's got, his name is Garrett Lisi. People should look him up. He's got a bunch of really interesting things. Let's see if I can play his little YouTube. There we go. Let's play this. This is Garrett Lisi, there's the spelling of his name. This is his depiction of a big symmetry group. The big symmetry group is called E8, and it's the last sporadic Lie group. That's just there we go. Red, green, and blue. That accounts for the color charges in the strong nuclear force. I forgot what's going on here in this little diagram. But anyway, inside this group, Garrett found a way to fit every one of the laws of physics. And you can see that this is a very rich and complex group. As you rotate things around, these little colors move around, but they maintain beautiful patterns, just the way I did with Rubik's Cube. And there it goes. It's boom, it snaps into something, and that when it snaps into something like that, it means we can focus attention on one of the 4 laws of physics. The weak nuclear force, the strong nuclear force, gravitation. How did he get around this Poincaré problem? Well, he found a paper from 1977. I've forgotten the names of the authors, but this stuff is all something you can look up. And he found a dodge around it. There's another kind of symmetry pattern called de Sitter symmetry, and that does fit. Boom. Once, instead of looking at the Poincare group, you look at it in de Sitter space, you can make everything fit. And hats off to the guy, he found it. And so you can see it's just, if you search for theory of everything, let's see. Let me show you. Here we go. There's a nice little wiki page on it, Wikipedia page. It gives you some of the details.
Mm-hmm.
But the bottom line from our point of view is that there's very good reason to believe that this unification settles the laws of physics, and it has this kind of nice, satisfying feel about it. That it's the last of the big Lie groups, the last of the exceptional Lie groups. There aren't any more out there. This is another little thing. Let me talk about that for a second. These are some gaming dice. One of the patterns of the gaming dice are the 5 Platonic solids. There are only 5 of these things. These are regular solids that where every face on the polyhedron is exactly the same. So there's a tetrahedron, a cube, a octahedron, dodecahedron, 12 sides, and octahedron, and that's it. There are no more. And you can prove there are no more. So isn't that interesting? There are only 5. What a strange number. We live in a 3-dimensional space. You could be accused. You could be excused for thinking there were 3 or 6 or 9 or something. No, 5, just 5.
Okay. So instead of 42,
the
meaning of everything is 5.
It's 5, or maybe it's E8.
Interesting.
Yeah, instead of 42, it's E8, and some of the magic numbers around E8 are 248. That's a number of vectors and some projections of it. 8. It's a symmetry group of operations in 8-dimensional space. And there are a lot of technicalities on it. It'll probably take me a couple of years to work out all the math on it, but that's okay. I'll take him on faith. I think,
okay.
And there are a lot of people looking at this. I have not personally worked out all the math behind this, but I have a really good feeling that he stumbled across it. But now we stumbled across something else.
Interesting.
So let me rewind to quantum mechanics for a second.
Okay.
Remember I said in quantum mechanics, particles act exactly as if they turn into a wave and they go everywhere and explore all the possibilities all at once, and then they come back to a destination point?
Yep.
Doesn't that sound a little bit like parallel computing?
Absolutely.
Yeah, yeah. So in the multi-core world, we get real excited about 2 cores and 4 cores and maybe 8, maybe 16.
Boring.
What about all the cores, all at once?
All core.
How about all core? How about billions and billions and billions of cores all at once in parallel? Suppose you could somehow encode a computation in a quantum system, let it rip, let it go everywhere all at once, and converge back and give you the answers. You could go faster, you could solve bigger problems, but the problem is, how do you encode an arbitrary computation in a quantum system? And how do you collect the information back when you're done? Well, let's talk about the encoding problem. Remember I said that Platonic solids, there are 5 of them and that's it, there are no more? E8, that's the last Lie group. That's the biggest one. There are no more. Well, is it big enough to encode anything? Is E8 Turing complete? Can we put a programming language inside E8? Is there enough room left? And the answer is yes, there is. And we found it. He found that all the laws of physics fit in there. That means that laws of quantum mechanics fit in there. That means that we can correlate, if we can encode a computation inside a representation of E8, and we can find a way to map this to a quantum system that explores all the possibilities at once, then we can take a gigantic parallel computation and have it run on as many cores as we want. You don't have to be stuck with 4 or 8 or 16. You can. It goes everywhere. It goes forward in time. It goes backwards in time. It goes into Alice's mirror and out the other side. And you know, there's absolutely no limit. So this is free computation plucked out of thin air. Free.
Interesting.
And we found it, thanks to Garrett and the theoretical physicists. So that's all I can say.
Okay.
That's all I can say is we know how to encode any problem inside a representation of E8. This turns into some matrix computations, and you know, matrix computations are very rich. They're almost, you know, if you think about the lambda calculus or about Turing machines, you can almost scratch your head and say, you know, I could probably encode that in a matrix computation. Try to do it, you'll stub your toes a few times. But if you have this intuition that's provided by this grand solution of everything, then it just turns out it's just sitting right there. It's just sitting right there. Yeah, so you may not be able to find it, and your Niners may not be able to find it, but we clever little bunnies here at Microsoft, we found it.
You found it.
We found it. So we can encode any computation inside E8. We can convert that into a quantum mechanical system. It turns out that the system that we're going to experiment with, okay, so I'll drop a little more information here. Imagine a gigantic tank filled with Freon. Or this old fluid that was recently out, dry cleaning fluid. I'm trying to think of chlorofluorocarbons. I'm not the chemistry guy on this project,
sure.
but chlorofluorocarbons and dry cleaning fluid. Somebody out there in 9-line will remember that.
There's some chemistry.
Yeah, there's some chemistry. Okay, you cool this stuff down to almost zero. Okay. You know, as close to absolute zero as you can. It becomes superfluid, becomes superconducting, becomes highly quantum mechanical. In the input side, we write down our little equations, our little matrix equations for encoding this. They're big matrix. They're 248 by 248 plus complex numbers and quaternions and all this kind of stuff. They're intricate but straightforward. Encode your computation, whatever it is, stick it in this vat of trichloroethylene, or I think that was it. I think it popped out.
Nice.
and let it rip.
Organic goop.
Some organic goop.
Got it.
Illegal chemicals, you know.
Okay.
They used to be legal. They used to be in every dry cleaner and in every air conditioner in the world. But you know, in the laboratory we can keep them contained, and let it rip. And it explores all the computational possibilities at once, as many cores as you want, and out the other end comes your answer.
Interesting.
And it doesn't matter how big the problem is; it'll just find more processors. These little supercooled molecules that are moving around, these superfluid molecules, there's enough room there to solve any. You know, okay, so if you run out of room, if there aren't enough billions and billions and billions of particles, molecules available for your computation, then just buy a bigger tank.
Okay.
Plug it in, collect out the answer. Now, the part that's not quite solved yet is we don't know how to print out the answers. We know how to put them in.
Yeah.
We know that the computation is correct because we can do all of the theory from starting at point A and going to point B. But collecting the answers at the end is our open challenge. But
interesting.
once we collect them, then we can visualize them. We can print them out. You know, imagine plugging this into an Excel spreadsheet, so that in the future, if you have a really big solver scenario for Excel, we'll sell you a tank of trichloroethylene.
Okay.
And a cooler.
Yeah. Excellent.
Why are you laughing? You plug this into the dongle and maybe even the USB port.
Interesting. It just seems pretty remarkable.
Yeah. Microsoft branded tanks of supercooled trichloroethylene for parallel computing. Forget all this multi-core stuff.
Agreed.
Yeah.
It seems to be overhead anyway. It's too complicated.
It's just overhead. Yeah. I mean, a little bit of supercooled Freon is...
Excellent.
Yeah.
So what's the name of this project?
It's called April Fools.
All right. Nice one. Nice one.
All right. Thanks, Charles.
Thank you.
All right.
We'll talk to you again soon.
Cheerio.
Cheers.